Welcome to video 6.1a, an introduction to collision theory and rates of reaction for topic 6. Yeah, I told a chemistry joke today, but there was no reaction. The activation energy barrier must have been too high. Yeah, that's it. In terms of accessing prior knowledge, concentration will be a helpful term to remember. Remember, concentration, we typically use moles per decimeter cubed as the standard IB unit for concentration. And your work on the Maxwell-Boltzmann distribution curves introductory activity. This is a look at 3 different temperatures, the same gas, same pressure, etc. at 3 different temperatures. So the higher temperature has a bigger spread in terms of the velocities of the gas particles. With more of the gas particles having a higher velocity, the average is going to be higher as well in terms of the molecular velocity. The big idea is the greater the probability that molecules will collide with sufficient energy and proper orientation, the higher the rate of reaction. If you increase collision frequency, you will increase the rate. Collision frequency is an important thing because, let's just make up an example. If I have 10 collisions per millisecond, and I wait 10 milliseconds, I'll have 100 collisions. But if I wait 20 milliseconds, I'll have 200 collisions. I had more collisions, but I'm not going to have a faster rate at 20 milliseconds. I need to increase the collision frequency in order to increase the rate. Couple understandings. Obviously, in terms of the kinetic theory and Maxwell-Boltzmann energy distribution curves, we will need to use those in our discussion throughout this particular video and topic. Kinetic molecular theory: a gas consists of a collection of small particles traveling in straight line motion and obeying Newton's laws. When they collide, they bounce. The molecules in a gas occupy no volume, approximately like an ideal gas. Collisions between molecules are perfectly elastic. No energy gained or lost during the collision. Obviously, these are kind of assumptions. They're ideal assumptions, if you will. There are no attractive or repulsive forces between the molecules, again, in an ideal scenario. This last thought, though, is quite important. The average kinetic energy of a molecule is 3 kT divided by 2, where K is the Boltzmann constant, Boltzmann, and T is the temperature in Kelvin. So that means temperature is a measure of average kinetic energy of a group of molecules. And these are the Maxwell-Boltzmann distribution curves. So as I increase the temperature, the average molecular velocity, the average kinetic energy of these group of molecules will increase. Increase the temperature even more, I'll get a bigger curve that's wider with an average even higher. Species react as a result of collisions of sufficient energy and proper orientation. And activation energy is the minimum energy that colliding molecules need in order to have successful collisions leading to a reaction. So if I think about some generic reaction, A reacting with some molecule BC, so this is A plus BC makes AB plus C. Then the collision has to be with A and B. If A collides with the C end of the molecule, it won't make AB. So not only do the particles have to collide, but they have to collide with the proper orientation and enough energy to make the reaction happen. And that minimum energy requirement is called activation energy. The official IB definition from previous exams is the minimum energy needed for a reaction to occur, or the minimum energy difference between reactants and the transition state. If we look at enthalpy diagrams, this is the activation energy. It is the energy difference between reactants and the transition state. And here's another look at activation energy for maybe a little bit nicer drawings than what I just drew for you. This is an exothermic reaction. The products are more stable than the reactants. We have a negative delta H. This is the activation energy barrier. For an endothermic reaction, it's typically a larger activation energy barrier because from reactants to the transition state, it's typically a larger barrier. This is a look at the transition state. If I have 2HI and I need to make H2 plus I2, maybe the H and the HI molecules need to collide so that I can get H2 and I2 in that fashion. And so when they collide and bonds are forming and bonds are breaking, that's called the transition state. And this is HBr. And these are going to be your H2 and your Br2. So this is a look at a couple specific reactions. Particle collisions must be with enough energy and with the right orientation. So maybe the collision is too gentle, nothing happens. Or maybe there's enough energy, but it's the wrong orientation. So here I have enough energy, and I have the proper orientation. So this is some generic reaction where 2AB is going to react to make A2 plus 2B particles. So not only do I need enough energy, but I need the proper orientation. So not all collisions will be successful collisions. So if I look at a Maxwell-Boltzmann distribution curve, some amount on the x-axis, some amount will be the activation energy. And so these are the particles that have enough energy so that if they collide, they will have enough energy to overcome the activation energy barrier. Doesn't mean they will react because they might not have the proper orientation. But these are the molecules or particles that have enough energy to be higher than the activation energy required for a reaction. And obviously this is just a generic table. I don't know what it is for a specific reaction. It'll be in a different location for specific reactions. Rate of reaction is expressed as a change in concentration of a particular reactant or product per unit time. Typically, the concentration of a product will increase quite dramatically and then level off over time as the rate slows down. Or the concentration of a reactant will decrease over time until the reaction stops. So rate of reaction is the increase in product concentration per unit time or the decrease in reactant concentration per time. So it's delta concentration of products divided by delta T or negative delta reactants divided by delta T. And the typical units for rate are moles per decimeter cubed per second. Moles per decimeter cubed per second. So catalysts decrease the activation energy by providing an alternate pathway. Catalyst provides an alternate pathway for a reaction that has a lower activation energy. Catalysts are not permanently chemically changed. And so let's look at this in relationship to energy profiles and Boltzmann distribution curves as well. So here's an energy profile or an enthalpy profile. If this is the uncatalyzed reaction, it has quite a large activation energy. If there is a catalyst present, it will have a significantly smaller activation energy because there will be an alternate path. Catalysts often help the number of collisions that are successful to increase in terms of frequency because they improve the orientation of the molecules when they collide. That's a very common mechanism for catalysts. We will investigate mechanisms a little bit later on in terms of how reactions happen. In terms of the Maxwell-Boltzmann distribution curve, if this is the number of particles that have the activation energy when there is no catalyst present, the catalyzed activation energy will have a lower activation energy, which means more particles will have the required activation energy. So a catalyst increases the probability of a collision having an energy greater than the activation energy. And if I can increase the probability of a collision having energy greater than the activation energy, I will increase the rate. And there you go. That's your introduction to collision theory and rates of reaction. In TOK connection, the Kelvin scale of temperature gives a natural measure of the kinetic energy of a gas, whereas the artificial Celsius scale is based on the properties of water. Are physical properties such as temperature invented or discovered? It's an interesting one. International mindedness, ozone depletion. We talked about that a couple different places and how that certainly is something that affects the world. Nature of science. This is going to be really important for mechanisms. And the most simplest theory is often the best explanation. In terms of connections to other topics, it relates a little bit to energetics, the unit we just had, and activation energy. Solutions in stoichiometry are important throughout this unit. And of course, a little bit about the particle model and the kinetic molecular theory from our work in topic 1. As a summary, got some space on your notes handout for the summary. Rate of reaction measures the change in concentration of the products or reactants in a reaction. It is affected by numerous factors, which we'll discuss later. In order to increase reaction rate, the frequency of collisions and/or the energy available in these collisions must increase. And catalysts provide an alternate pathway with a lower activation energy. And that's your summary. Checkpoint question. Multiple choice question 1. I would love to see more than a couple entries into the Google form. Which of the quantities in the enthalpy level diagram below are affected by the use of a catalyst? 1, 3, 1 and 2, or 2 and 3? Figure out your answer and come back. Check your work. And the correct answer is C, 1 and 2. If I have a catalyst, the enthalpy curve will look like this. And so that means 1 will be affected, which is the activation energy. And 2 will be affected, which is essentially the activation energy of the reverse reaction, or the energy released in bond formation. This energy is bond formation. This energy is essentially bond breaking. The overall delta H, which was 3 in this diagram, is not affected by a catalyst. One more multiple choice question. Which statement is correct for a collision between reactant particles leading to a reaction? Take a look at your choices. Make the best choice. Pause the video. Come back for an answer. Pause the video. And the answer is C. Colliding particles must have a kinetic energy higher than the activation energy. Let me know if you have any questions about these. You can put them in the Google form. I'd love to see some responses in the Google form. Even if you don't have questions, show me your answers to the 2 checkpoint questions. 6.1a on the Google form. Thank you very much. Have a great day. See you in class.